Alright class, in this video I'll be introducing the second derivative test and how it applies to a polynomial function. Let's begin. So we're going to let the second derivative exist on some open interval containing c, except possibly at c itself, and we're going to let the first derivative at c equal 0. 1. If the second derivative at c is greater than 0, then f of c is a relative minimum. If the second derivative at c is less than 0, then f of c is a relative maximum. If the second derivative at c is 0 or does not exist, then no information about extrema is given, and we have to go back to the first derivative test that we discussed in section 13.2. All right, so why are these first two statements true? Well, if we take a look at statement 1, notice that the second derivative is greater than 0. And that means the graph is concave up. So the critical number in that interval is going to be a relative minimum. If we take a look at the second statement, the second derivative is less than 0, which means the graph in that interval is concave down, so that the critical number in this interval, where the graph is concave down, is a relative maximum. So how does the second derivative test apply to a polynomial function? Okay, so we want to apply the second derivative test to this polynomial function right here. And the first thing we're going to want to do is take the first derivative. So the first derivative is negative 6x squared plus 18x plus 168. Next, we're going to find all values of x where the first derivative is equal to 0. So I'm going to set the first derivative equal to 0 and solve for x. All right, so when x is equal to 7, and when x is equal to negative 4, the first derivative is equal to 0. So that means the first derivative at 7 is equal to 0, and the first derivative at negative 4 is equal to 0. So that was the first part of the second derivative test. Now, to actually take the second derivative test and apply that test to this derivative, to this function. All right, so the second derivative is the following. So what I'm going to do is I'm going to evaluate x is equal to 7 and x is equal to negative 4 in the second derivative. I'm just going to create a little bit more space. So the second derivative at 7 is equal to negative 84 plus 16, which is clearly less than 0. All right, so what we can conclude is that since the first derivative at 7 is equal to 0 and the second derivative at 7 is less than 0, there is a local maximum at x is equal to 7. the value is, and I'm going to get that value on Desmos. So I already have the function in Desmos, and I'm going to evaluate f of 7. And that is 928. And to see that that point actually does lie on the function, you could see it is indeed the location of a local maximum. So the value is 928. Okay. Now to test x is equal to -4. So the second derivative when x is equal to -4 is equal to the following. Oops, that's going to be 48. That's clearly greater than 0. So since the first derivative at -4 is equal to 0, and the second derivative at -4 is greater than 0, there is a local minimum at x is equal to -4. The value is, and I'm going to get that value on Desmos right now. So it looks like -403. And just to make sure that that coordinate lies on the graph, I'm going to type the coordinate into Desmos. And indeed it does. It is the location of a local minimum. And we have successfully applied the second derivative test. And we did that with this statement right here. Oops. And with this statement right here.